9.4, the comparison of series. Alright, let me go over the first definition. Theorem 9.12, direct comparison test. Alright, we have two series, A sub n and B sub n. Alright, B sub n is bigger than A sub n, and A sub n is greater than 0 for all n. The theorem said if the series of B sub n is converges, then series of summation of series of A sub n is also converges. It should make sense to you because B sub n is bigger. So if the bigger one is converges, the smaller one is also converges. Alright, let's look at the next one. It said that summation of A sub n is, if it diverges, then the summation of B sub n is also diverges. And this is same idea. If A sub n, which is the smaller one, is diverges, then the bigger one should be diverges. Alright, I put summation here that I just explained to you in the box here. So if the large series converges, then the smaller series also converges. The smaller series is diverges, then the larger must also be diverges. Alright, so let's look at our first example. Alright, use the direct comparison test. This is called the direct comparison test to determine the convergence or divergence of series. Alright, I have this summation of this series. Alright, 1 over 3 n squared plus 2. So you're going to compare to something that easier to do the test. So look at the one I use. I pick 1 over 3 n squared. Try to pick something that's similar to this one so it's easier to compare. You see the denominator here is bigger because you add 2 to it. This one is just 3n squared, this one is 3n plus 2. So if the denominator is bigger, the whole thing is going to be smaller. So I can say this is smaller than this. Alright, don't pick something that completely opposite, different. So you can compare this easily, that this whole thing is smaller than this one. Alright, so I'm gonna test this one because it's more difficult to test this one and then apply theorem 9.12. Alright, so I write down summation n from 1 to infinity, 1 over 3n squared. I'm gonna factor out the constant, which is, I take it out, 1 over 3 sigma n from 1 to infinity, 1 over n squared. Alright, I'm just bring out the 1/3. Now you can see this sequence here is P series. Alright, we covered that in the last section. This is P series. So my P series, this is theorem. Alright, this is from theorem 9.11 P series. Alright, if you don't remember, go back to the previous section, P series. So my P is equal to 2, which is greater than 1. This is my P right here, is equal to 2, is greater than 1. So this implies that this is converges. Again, if the bigger one converges, the smaller one must be converges from the first property here, theorem 9.12. Right? So therefore, sigma n from 1 infinity, 1 over 3n squared plus 2 is also converges. Alright, now let's look at my next example. Alright, I have the sigma n from 0 to infinity, 4 to the n divided by 5 to the n plus 3. So I have to pick some rational function that similar to this. I pick 4 over n quantity to the n is similar to this. But look at the denominator. I have 5 to the n plus 3, right? And 5 to the n. Actually, I make a mistake. This should be 5. Alright, this should be 5. Because I want to be close to this one, similar to this one. Alright, so this 5 to the n plus 3 is bigger than 5. So this whole thing is smaller than 4 over 5 to the n. And I'm going to use this to test. So sigma n from 0 to 1, I rewrite this as 1 times 4 over 5 to the n. Alright, if you remember, this is geometric series. Alright, my a is 1, my r is 4 over 5. Alright, and then the summation of this is just a over 1 minus r. Again, my a is 1. Alright, my r is 4 over 5. If you simplify this, it's equal to 5, which is converges. Alright, so if the bigger series is converges, the smaller must be converges by this theorem 9.12, the first condition. Alright, so this sigma n equal to 1 to infinity, 4 to the n over 5 to the n plus 3 is converges. Alright, let's look at the next theorem. Hey everyone, let's come back to our 9.4. Let's finish our 9.4. Alright, the next theorem is theorem 9.13. This is called limit comparison test. The technique of this test is different from the direct comparison test. Alright, so if you have a sub n greater than 0, b sub n greater than 0, and if you take a limit as n go to infinity and put a sub n divided by b sub n, and you get some number which is finite and positive, then you can conclude that if one of them is converges, the other one always also converges. If one of them diverges, the other one also diverges. Right? So let's look at our first example here for this theorem. I have this series here. Alright, 5 over 4 to the n plus 1. I call this one a sub n. Now I'm gonna let my b sub n is 1 over 4 to the n. From the previous theorem, we want to find something bigger or smaller, but we're not trying to do that here. We want to find something that if we put them in ratio, we get a finite and positive. Alright, so I pick this one. So I take a limit as n go to infinity, a sub n over b sub n. Alright, I use substitution here. Then I get this one. Alright, I want to show you that I will have a finite and positive. From here, I divide both numerator and denominator by 4 to the n. If I do that, the numerator, these two terms just cancel out. I left with 5. The denominator, this first term, I just get 1. And the second term is just 1 over 4 to the n. Alright, now as n go to infinity, 1 over 4 to the n will be 0. So this whole thing is 5. 5 is finite, it's positive. Alright, it satisfies our condition here from the theorem. So I have to prove one of them. If one of them is diverges, the other one have to be diverges. If one of them is converges, the other one have to be converges. So I will make it easy on myself. I pick the easy one, which is b sub n. Alright, that's easier to prove. From this one, I rewrite it as sigma n from 1 to infinity, 1 times 1 over 4 to the n. Alright, I know it's converges from the geometric series. Put in the right form, my a is 1, my r is 1/4 to the n, and my absolute value of r is between 0 and 1, strictly less than 1. So it's converges. So since my b sub n is converges, my a sub n must be converges by theorem 9.13. Alright? Let's look at the next one. Alright? The next one, I have this series. Alright? So I let my b sub n is equal to 1 over 2 to the n minus 1, which is very similar to this one. and again I put them in ratio, limit as n go to infinity, a sub n over b sub n, alright, reduce to the n minus 1, alright. I left with n for the numerator, n plus 1 on the denominator, alright. Next step, I divide everything by n. So if I divide everything by n, on the numerator I would have 1, denominator I would have 1 plus 1 over n, alright. As n go to infinity, the second term on the denominator will go to 0. So this whole thing is equal to 1. Again, 1 is finite and positive. I satisfy the condition on the theorem here. So I have to pick one of them and see if it's converges or diverges. So I pick the easy one again, this easier one actually. So let's see, which one did I pick? I pick b sub n. Alright, b sub n, this is my b sub n. Alright, I rewrite it. As you can see, this term and this term are the same thing. Alright, I'm just rewrite it to fit my geometric sequence. So my a is 1, my r is 1/2, alright, to the n. So my r is between 0 and 1, so that means the sequence is, the series is converges, so the original one is converges. So when you do the homework, make sure you write all the detail, alright, how do you simplify it, and make sure you prove that it's finite, it's positive, and which theorem that you apply. Alright, so we finished 9.4. I'll see you next time.